Hello everyone, I'm Jaeger Chu, one of the instructors of this course. So in this week, continuing from the attention model, we will study another really hot and popular model called a generative adversarial networks. So overall, we will cover how this generative adversarial networks work, and then also as its a representative example, we will discuss the deep convolutional generative adversarial network, or in short DCGAN, for the mainly image generation tasks, and also another extended model called a cycle-GAN, which can be viewed as the task of this image translation. And here's the overview of generative adversarial networks. So the main purpose of this GAN, or generative adversarial networks, is that given a data set, which is our training data set. For example, let's imagine we have a set of facial images, and then our main purpose is to generate fake but really realistically looking facial images. So now our GAN, or generative adversarial network model, is trying to generate really high quality images that mimics the reality that is found in this set of given training images, which is in this case facial images. And so that's why we call it as generative networks. But why is it called adversarial? So in this model, we actually build two separate models called a generator and discriminator. And let's think about this scenario of a spam email generation company. So yeah, certainly this is a bad company, but this company's main goal is to generate the spam email that just looks like a really real email that can avoid this spam filtering mechanism in many email clients. And then now we can view another counterparty, which is like Gmail's spam email detection module or filtering algorithm. And then the main goal of this discriminator part is to try to accurately detect a spam email even though it looks like a real email. Okay, so that way this spam email generating company and also Gmail's spam filtering algorithm or module will have some adversarial relationship. So that's why we call it as adversarial networks. But based on this adversarial relationships, each party or each side of these two modules will try to improve their own module. So as this discriminator or spam email detection algorithm becomes more and more capable of detecting a spam email, this spam email generating company should be able to generate higher and higher quality spam email that looks more like a real email. And given the improvement, this high quality spam email, this discriminator part should also be able to improve their own algorithm to filter out these spam email even though they looks like a real. And now let's look at more details about how this GAN works in the context of image generation tasks. So given a set of real images, our discriminator part should be able to classify this image as a real image, right? And then in this case, our discriminator, which is its own neural network, will be designed as a binary classifier that has the high value output for given real images. And then we can train our model by using this real given set of real images. Now let's turn to another network called this generator that plays a role of generating a fake image but that has to be looking as a real images. So that is the goal of this generator network. But typically, in order to generate different images in different times, we give a random vector generated from typically some Gaussian distribution that has a zero mean and unit variance. And suppose that Gaussian distribution generated vector has a 100 dimensions. And then we call it as a latent code or noise vector in this case. And then given this random vector as an input, this generator will create its own fake images. And then here the conflict arises between this generator and the discriminator. So given this fake input, this discriminator should be able to classify it as a fake images properly. So in this case, the classifier output should be close to 0, indicating that it is the fake images. But in the case of generator perspective, the generator should create this image so that it is the most indistinguishable from the real images to deceive the discriminator part. So from the perspective of this generator, it will be ideal that the discriminator output given this image to be close to 1 instead of 0. So that's where this conflict between these two network arises. This conflicting criteria from this generator and the discriminator can be represented as this single formula as an objective function of this generative adversarial networks. And then let's look at first the perspective of this discriminator. And in the case of discriminator, for the real images, it should maximize the classifier output of its own discriminator part. And so it would be great if the log of this classifier output to be maximized. So in this case of log function, it is just a binary cross entropy loss, but also it can be simply thought of as just a monotonically increasing function. So if this one gets maximized, and also log of it will also be maximized. And thus, this part, when x is the real data, and then it should be maximized. But at the same time, if this image x was actually the generated and fake output from our generator network, and such an output or fake image can be represented as this output of our generator, but when using some random Gaussian vector as z, which was our 100-dimensional vector in this case. And this is actually a fake image, and in this case, the output of this discriminator should be minimized. And overall, when considering this 1 minus this output, and then log of it, which is still a monotonically increasing function, and then this one will be maximized when this guy is minimized. And so overall, if we maximize this from the perspective of discriminator, and then it is corresponding to the situation where we maximize the probability for the real images, but also we minimizes the probability for the fake images. So that is the objective function of discriminator part. And then now let's look at the generator part. And in this case, generator is only involved in the second term. So the first term is actually independent of the generator. So that means from the spam email generation company, they cannot manipulate or change this discriminator part, which corresponds to spam email filtering algorithm that maybe Gmail has. And so this generator part cannot do anything on this discriminator network, but they can only improve their own generator part. So in this case, from the perspective of this objective function of this generator, instead of maximizing this part, it should minimize this part, so that this part becomes maximized, which means for these generated fake images, the generator will want this value to be maximized, and thus overall this part should be minimized. So that way we have this minimization operation here. So in this manner, we can train our own generator part or spam email generation algorithm, and then at the same time from the discriminator part, it can be trained so that it can properly classify whether it's a real or fake images. And let's look at a detailed implementation example of this generative adversarial networks, or GAN. So we have this discriminator and generator, and then suppose we have the MNIST digit image examples. So in this case, we will have 28 by 28 grayscale images, and then altogether, if we consider it's just a feature vector representation as just concatenated column vectors, and then the input image will be formed as 784, which is a 28 by 28 dimensional feature vector. And then for our discriminator part, let's consider it's a fully connected neural network that first reduces the dimension of this input vector into 128 dimensional vector internally, and then go through this nonlinear unit of ReLU, and then also another fully connected layer that reduces this dimension into one single scalar value. And then at the end, we will go through sigmoid function so that it can generate the output ranging from 0 to 1, and thus 1 indicates the 100 probability of being a real image, and 0 indicates like 0% or probability of being a real image, and at the same time it will correspond to 100% of being a fake image. And that way we can design this simple discriminator network. Then let's look at the generator part. In this generator part, we start with just a random 100 dimensional vector, and then taking that as an input, we can form a linear layer that actually expands the dimension first into 128, and then go through the ReLU as a nonlinear unit, and then in the next we will generate and expand 784 dimensional vector, and then we can use a 10H layer, and then we can reshape this output vector of 784 dimensional vector into 28 by 28 matrix, so that it can represent as a particular image. Okay, so that way, given this 100 dimensional vector, our generator network generated this 28 by 28 size of image as an output. And then let's consider this binary cross entropy loss, which is common in this binary classification network. And then here's the optimizer that we chose for our discriminator and the generator, and in particular we used something called ADAM, which is a variant of gradient descent algorithm, and then we have some learning rate. Okay, and then let's form some batch that is used to train one step of our neural network parameter update. Then suppose we pick up maybe 32 real images, and then our X, which will form our real set of real image, will form this size of a batch of 32 images in a 784 dimensional vector. And then also we can form the fake image side of 32 images of 100 latent vector that will be used as an input to this generator network. And then we iteratively update our parameters based on minimizing or optimizing this loss function. And in this case of these loss function can be viewed as the objective function that we studied in the previous slide. And then this one is actually the objective function for our discriminator network. So when given the real image X, and then the label, the corresponding label should be 1, which means these images are real images. And then in the case of these generated images, and then the output should be close to 0. So that's how we train our discriminator network. And then at the in the next step, we have to train the generator network. And then the generator network's criteria is this. So we want to have this generator output to be as close to as 1, which actually deceives that our generator, our discriminator, to think of our fake image as a real image. So the corresponding ground truth label is set as 1, and then through this backpropagation, we optimize the parameters contained in our generator network. So that way we iteratively optimize our discriminator and the generator part, and then those two networks will get continuously improved, and thus at the end our generator module will generate really realistically looking images, although it's just a fake images. And now let's look at another architecture for specifically this image generation tasks called a DCGAN, or Deep Convolutional GAN model. So in the previous simple example, we only used fully connected layers when discriminating an image, whether it's in about whether it's in fake or real images, and also for generation part, in order to generate 28 by 20 size of an image, we still used this linear or fully connected unit. But as we know, this convolutional neural network is quite effective in this image classification tasks and so on. And so we can design our discriminator part as a kind of convolutional neural network, and also for this generator network, which generates from this 100-dimensional latent vector into a particular image. And we can also utilize this convolutional neural network. But in particular, convolutional neural network actually extracted out some meaningful information from the images. And then at the end, it will shrink down the image sizes or activation map sizes so that it can extract out some meaningful information from some large regions. But we have to do this inverse process of this convolutional neural network in the case of generating the images. So that is called deconvolutional layer. So in that case, we have some layer called a deconvolutional layer, which works as the exactly an inverse process of a convolutional layer. So we have a one single particular value, and then it will be expanded out into a larger image patches. So if we imagine the convolutional process, it was exactly the opposite process. So that way we can attach those deconvolutional layer so that we generate this large intended size of an input that has this RGB channels. And utilizing this architecture, they improved this generative adversarial network architecture for this high quality image generation tasks, and that is called this deep convolutional generative adversarial network, or in short DCGAN. Okay, and then this is a high level architecture of this DCGAN. For the discriminator, as I briefly mentioned, it can be designed by using just typical convolutional neural network. But in this case, they particularly used nonlinear unit as this variant of ReLU called the leaky ReLU. And for the generator part, we use this deconvolution, which is the inverse process of convolution. And also at the end of the convolution layer, we put a nonlinear unit of ReLU. And then interestingly, they designed their network so that they have no pooling layer. And also they used this batch normalization and the variant of optimizer called the ADAM. And that way they generated this fake but realistically looking images. And by using this DCGAN, we can do some interesting arithmetic operation. So let's imagine some latent vector which corresponds to this 100-dimensional vector z, and let's imagine some vector generated this image which corresponds to a man wearing glasses, and then also suppose another vector z corresponding to the man without wearing glasses, and then let's consider another latent vector z corresponding to the woman without glasses. And then when just performing this subtraction between this vector and this vector, and then semantically this can be viewed as having the semantic meanings of wearing glasses, because the common part of being a man's image, they will be cancelled out from this subtraction operation. And then this semantic part of containing this wearing glasses, and then such a part can be added to the images, the latent vector that corresponds to the woman without wearing the glasses. And then after all, we will have the resulting vector z, and then we can use it to generate this images by using our generator network. And in this case, for various z vectors corresponding to different images for this category, and then we can generate the various z vectors, and then correspondingly we can use it as an input to our generator network to generate different images. And then interestingly, they generated all those woman images with the wearing glasses. So that way our vector z can contain those semantically meaningful information, and that's what this GAN network has learned from this training processes. And now let me introduce another model called a cycle GAN. So this is not pure image generation task, but it's just aiming at image translation task. So it starts with an input image, and then the goal is to try to convert this image into another image, but in a particular domain or particular characteristics. So in this case, let's look at the example. For those paintings of a particular style, and then we can think of as real photos. Okay, so in this case, it is like paintings, but this is corresponding photo. And given this image, and then we can convert it to a real scene like photo images, but also this photo can be converted into a painting with a particular style. And also we can think of some images containing these zebras, and then it can be converted into another images that contains just horses with brown colors. And also we can think of this inverse processes as well. And then we can also another transformation or image translation tasks between the same images but with the different in different seasons of winter and summer. So in this process, unlike the original GAN settings where we just provide a latent vector and then generate some random images, which is a fake but realistically looking images. But in this image translation task, we start with this original input image and then wants to generate its converted images in a particularly intended style of an images. And now our cycle again has this generator part which plays a role of image translation or conversion, and also the discriminator part that classifies whether a given image is real images in domain B. Okay. In this case, the discriminator will be just trained similarly to original GAN model. So for given these translated or fake images, you should be able to classify it as a kind of fake images from the perspective of those domain B, which corresponds to the horse images with the brown colors. Okay, and then also for the real images containing those horses with the brown colors, it should classify it as a real images. So that's how we train this discriminator part. But in the case of generator part, which is this translation model, should try to maximize or deceive this discriminator part by using this converted images. So that way this translator or generator part will try to maximize the probability of being real images in domain B by using their generated output. And additionally, this network in this cycle again has additional loss which is called a cycle loss. So in this case, we design another network that can now convert this images containing horses with the brown color back to this zebra images. So this part and this part are two different generator or image translation or conversion network, but the first one should convert this zebra images into the horse with the brown color, and this part will convert it back to this zebra images. But in this case, when passing through these two inversely related networks, and then what we want to obtain is the original zebra images. That is exactly the same as the input images. So we impose this loss so that these two images to be as close as possible to each other. So that way we can train properly these two image translation network to convert each given images into a corresponding domain. So this is called this cycle loss, and then altogether this generative adversarial network that plays a role of this image translation is called this cycle GAN. And at the high level, the point of this L2 loss is that this network tries to maintain the shape of this original zebra horses. So they try to change only the necessary part, which corresponds to the color in this horse region in our image. So otherwise, if it generates completely different horse images with just a brown color, and then it will be okay to set it, to deceive our discriminator part, but it will no longer be able to reconstruct this original given images. So that way, through this L2 loss, we force our generator network to maintain the original shape of this image. And let's look at these image translation example using this cycle again. And yeah, these cases are the translation between a zebra and horses. And then, yeah, between these two, the image translation quality is relatively high. And then also, yeah, in the case of winter images and versus the summer images, they, yeah, properly translated the images so that those translated images looks like the images in the corresponding seasons. And another example is the translation between some digits found in real world pictures. So these data set is called the Street View House Number data set. So we just take up photos from the real images where those house numbers are shown in different houses. And so these numbers will be quite noisy, and then they will contain various background and other parts of the images. And at the same time, we can think of this MNIST images, which has mostly a black background and so on. And then when training our cycle GAN between these two domains of an images, then these are image translated versions from these Street View house number data example into MNIST data domain, and then vice versa. Okay, in summary, in this lecture, we studied generative adversarial networks and how this GAN works. And then as a representative model, we discussed deconvolutional GAN or DC GAN, and also its extended version for the image translation tasks called a cycle GAN. Okay, thank you very much.